Okay, everybody, this is a snapshot video on hypothesis testing. So once again, you should be familiar with this particular topic, having read over lecture notes, the book. Also, you should have read the first couple of pages here of the snapshots where I actually summarized this particular topic. Okay, so again, I assume that you're also familiar with working with the tables. All right, so I'm going to get right to the problems. Again, this is unedited. Hopefully I catch any mistakes as I go. But again, you will let me know if there is some sort of calculation mistake. The concept, the theory is going to be correct. All right, but again, hopefully I caught any particular mistakes in terms of calculation. So, once again, read this over, get yourself familiar with it. I'm going to get right to the problems here. You should always work the problems and then watch the video, okay, to compare your results to mine. All right, so anyway, let me get my pen working here. Let's get started here. Suppose a new process has been installed at the factory. So we're talking about the light bulb factory, right? And we want to introduce a new process which we hopefully will improve the expected lifetime of our light bulbs. So we've installed this process at a factory, one of our 3 factories, and in the past we have experienced a mean life of 920 hours, along with a standard deviation of 50 at this particular factory. So our population mean is 920 and standard deviation is 50. I took a sample of 20 bulbs and this resulted in a sample mean of 945. I am claiming that the new process actually increases the life of the light bulb. And I want to test this at a level of significance of 0.01. So here's what's going on here. Again, currently, the average life of a light bulb is 920 hours, right? Now, I've installed this new process at the factory, and I've taken a sample, and that sample resulted in a sample mean of 945. Is this sufficient enough for me to make the argument or make the claim that the process is actually improving the life of the bulbs? Now, when you take a sample, you know that the sample mean is not representative of the entire population. So you take different samples, you get different sample means, right? But what do we expect? We expect the sample mean to be within a reasonable distance of the true population mean, correct? That's what the central limit theorem tells us, right? So basically, what I'm saying here is that there's going to be a range of values our sample mean will take on, right? But there's going to be a certain point such that if we're significantly far enough away from what we think the population mean is, that should draw our suspicion that this actually is the true population mean, right? And therefore, we might, or it might suggest that maybe this is not the true population mean and that it might be further over, closer to where the sample mean is located, right? But again, no matter what, we know that the sample mean is not necessarily going to be right smack on top of the true population mean, but it's going to be within a reasonable distance of that population mean. So that's where the level of significance comes into play. If we work with the assumption that 920 is the true population mean, then there's going to be only a 0.01% probability that our sample mean is significantly far away. What we mean by that, well, we'll explain that in the particular, when we work out the particulars of this problem here. But again, that's the idea that I'm trying to get across to you in the notes above. All right, so I'm going to erase this right quick here so we can get started with the problem. And again, I'll try to re-emphasize what I just said here, all right? Since I'm trying to do this in a very short, quick video. All right, so the first thing we do is we state the hypothesis. The null hypothesis is always what I like to say is the status quo. In this particular problem, the status quo is nothing has changed and our population mean is 920. The alternative hypothesis, H1 or HA, depends on what book you work with. I work with H1, is the claim we are making. And our claim is that the population mean is going to actually increase, so it's going to be larger than 920. So there is our hypothesis. H0, to me, I like to say the status quo. H1 is what we are claiming to have to be different, right? Remember, there are three possible alternative hypotheses, right? Something increased, something decreased, or simply it's different. The second thing we're going to look for is the region of rejection. Remember, we work with the assumption that the null hypothesis is true, okay? But there's going to be a certain point where if that sample mean is significantly larger than what the null hypothesis is stating, then we're going to reject, correct? Meaning there's going to be some number out here, such that some point out here, such that if we're beyond that particular point, that suggests, you know what, something must be different here, right? Now, that particular value is either going to be a z-score or it's going to be a t-score. If you know what the population standard deviation is, you work with the z-table. If you're talking about a proportion, you're working with the z-table. If you do not know the population standard deviation, you're working with the mean, then you are working with the t-table. Here, I know what the population standard deviation is, okay? It's 50. So I'll look up in the z-table, and I'll look in the z-table associated with, again, you can look at the t-tables typically. Again, I'm not discussing the tables and where I find the values in the tables. That's for you to take care of. We're assuming that you can do this already because it depends on the table you're actually working with. All right? So anyway, if you look it up, you're going to find the z-score is going to be 2.326. That's associated with a level of 0.01, right? Okay? That is, if this were the true population mean, then the chances the sample mean is way out here is going to be 0.01. All right, so there's our region of rejection. Our test value is, quote, how do we get to the table, right? Since we're working with z-scores, our test value is z equal to x bar minus the null hypothesis mean divided by sigma of x bar, correct? So we do our math. We get sigma of x bar. That's going to be equal to 50 divided by the square root of n, which is 20. If you do the math, you get 11.1803. All right, so we know that x bar in the problem is 945. The null hypothesis mean is 920. The standard deviation for x bar, 11.1803. We do our math, and our test value comes out to be 2.2361. Now, with respect to the rejection region, 2.2361, change the color of my paper here, my ink here. This is actually located somewhere below this particular number, right? All I need to do is get a very general idea where it's located in reference to this cutoff point, right? So it is not in the region of rejection. So we do not reject, okay? We do not reject. That is, The information does not suggest the new process actually improves things. But we could have committed a type 1 error, right? I'm sorry, a type 2 error. I'm sorry, type 2 error. When we do not reject, it is possible that we should have rejected, right? And that is a type 2 error. All right. Now, in part B, we're working with the same problem, but we're going to change our level of significance to 0.025, all right? That means what we're going to do is we're going to look at a slightly different rejection region. Let me get my black pen working again here. That is, once again, there's going to be a point such that if we are above that point, we are going to reject, correct? At a level of 0.025. That is, again, under the assumption of the null hypothesis, the probability the sample mean turns out to be in this region is going to be 2.5%. Once again, we're working with a z-table, so this is a z-score. If you look up the z-score, you should find that is 1.960. Our test value calculation is no different. This is not a problem about a different sample. This is a problem where we're just working with a different level of significance. The probability of committing a type 1 error, correct? That's basically what the level of significance is, right? So, if we look at our test value from above, the test value from above came out to be 2.2361. That value is over here. It is in the rejection region, so here we do reject. And we reject with the probability of committing a type 1 error, right? That is what we're looking at. We do reject. That is, at this level, the data is suggesting that we should reject the null hypothesis. The process actually improved things, right? Okay? But notice that we have a greater probability of committing the type 1 error here. Okay? So we do reject in this case. All right? All right, so we're going to move on to the next problem. Once again, stop your video and work the problem, and then start the video up again. All right? So probably after this problem here, what I'm going to do is I'm going to create a second video because I don't like my videos to go over 20 minutes. All right, in this particular problem here, you read it, okay? What's going on is that the typical mean height of a U.S. male is 69.4 inches, right? But public health officials feel that older males tend to be shorter. They're claiming that older males, their average height is not this, right? That they're actually shorter. So again, the null hypothesis is basically the status quo. That the mean actually is 69.4. The alternative hypothesis is typically associated with the claim. And the claim here is that the mean for older males is actually below 69.4. Okay? So we went out and took a survey. Okay? And we got some information, but I'll read. Well, I don't know what I'm saying right now. Again, this is unedited. All right, I want the rejection region. Okay? The rejection region, in this particular case, again, we're claiming that the mean is actually lower. So, again, if our true mean is somewhere over here, then we're going to reject if the sample mean is significantly below this particular number, right? Again, we're looking for the mean being less than. Remember, the rejection region is always tied to the alternative hypothesis, right? All right, so getting back to the problem. Once again, if we look at this problem here, we do have the population mean and standard deviation. So we're going to be working with the z-score, right? We look up the z-score associated with a level of significance of 0.005. That z-score turns out to be 2.576. But the fact that we are on the left side of 69, we know that this is really a negative z-score, right? Be careful. So we're really working with the negative z-score here because we're on the left side. We are below the mean, right? Our next step is to calculate the test value. In order to calculate the test value, we need to know sigma of x bar, which is sigma 2.84 divided by square root of the sample size, 300. Do your math, and you get 0.1639. So our test value is, again, how we get to the table. Sample mean minus the assumed mean, null hypothesis, right? Divided by sigma. Do your math. And when we do our math, we get negative 3.6608. All right. So again, this particular number in relationship to our rejection region falls in the rejection region. So again, our conclusion is we reject, okay, the null hypothesis. So the suggestion is based upon the sample and our level of significance. Those two things come into play here, right? We're going to reject the hypothesis that there is no difference between the heights of older men and younger men, right? So we reject the null hypothesis, and we have the possibility right, of committing a type 1 error, right? You need to know your errors. Type 1 is rejecting when you should not have rejected. So we did reject, so it's possible that we shouldn't have rejected, right? But based upon the sample and based upon the level of significance, we're going to reject. All right, I'm going to stop this video here, save it, and then I'm going to have a second video because we're reaching the 20-minute mark. Okay?